2022. My name is Kingsley from Center for Corporate and Community Development, University Tunku Abdul Rahman, Utah. Today we are presenting a webinar titled Reconfigurable Origami is Changing the Landscape of Industrial Revolution 5.0. Are you ready for it? By Mr. Kenneth Cheng. Mr. Kenneth is the founding president of the Malaysia Origami Academy and the Malaysian Origami Association. He is also the pioneer of the Malaysia Origami movement, which resulted in the creation of over 120 Malaysian culture heritage origami intellectual properties. He conducted more than 8,000 origami workshops, lectures, exhibitions, and talks in Malaysia since 2014. Just a little housekeeping before we start. If you have any questions, please type them into the chat box in your Zoom control panel. I will bring them up during the Q&A session at the end of this webinar. For Utah students and staff, please sign in your attendance in the chat, posted in the chat box. Without further delay, let us turn the time over to Mr. Kenneth.
Thank you, Kingsley. First of all, good morning to everyone, and congratulations to e-KLESF Steering Committee and Committee for a successful launch. And my topic today is a reconfigurable origami, and this is actually changing the landscape of Industrial Revolution 5.0. And today I'll be sharing with you the development progress in the industry, as well as in the intellectual property landscape, so that you are better prepared and better informed of what are happenings and what will be happening. All right, so the fact that the e-KLESF arranged me to be the first speaker, I think is a good recognition of the importance of the technical origami plays in the high-tech industry. So without much ado, let me share with you what are all those origami technology that is happening around the world. First of all, origami is actually a very ancient paper folding art, as well as science. So in Japan, it can be traced back to about 220 years ago in a very ancient scripture. And in this ancient scripture, it's called the Zambazuru Orikata. You can actually Google it, and you can see every single page of the content in the internet. It actually contained much more than that. It contained the recipe in the crease pattern form, and it's quite technical in the sense that it utilizes a lot of mathematics and geometry to achieve a certain design objectives. So for those of you who are interested to dwell down deeper, you can do a Google by searching the term Zambazuru Orikata. All right, as you can see on the screen now, this is actually a crease pattern or the folding pattern of the crane that most of you have folded before. And if you put it into a finite analysis software, you will see that if you're following this crease pattern to fold into the crane, you can see the stress area, the hot spot, which part of the crane experience or undergoing stresses. And when you change over to material other than paper, be it metal sheets, plastic sheets, fabric, wood veneer, or even down to molecular level, then you have a good working principle and idea of how it affects the structure of the folded stage. The next slide is actually summarizing just very quickly for you a very generalization of the crease pattern analysis landscape. It has a simple and also a complex, but all of them comply to one piece of uncut paper. It can be a paper or any media nowadays. So if you can take a look at the simple and the complex, and you can compare the complexity and the density of the creases, you can see how it can achieve the shape without having to cut or even to glue the piece of paper. All right. Having that in mind, let's go and take a look at the landscape nowadays. So we are at the stage of Industry 4.0, in the stage of implementing all the Industry 4.0. And if you take a look at from Industry 4.0 to Industry 5.0, you can see that there is a lot of stresses on human integration into the current Industry 4.0 elements. So I will not go down to explain into what are the differences between Industry 5.0 and 4.0. You can search through the internet. There are abundant of information there. So I will just focus from Industry 4.0 to Industry 5.0. What are the roles of a deployable or reconfigurable origami plays, so that you have a better understanding and better informed on the direction. If you are doing research, if you are small businesses or even a corporation, at least you know the direction that the market as a whole is moving, all right? So the next slide is just very quickly to summarize from 4.0 to 5.0. And if you take a look at the element under the 5.0, you can see a lot of human integration back into the elements of 4.0. So a lot of customization, a higher level of customization, and a lot of localization of those elements. So I will go deeper into explaining to you and also point out to you some examples of how origami, the techniques have been utilized into all these elements. So if you take a look at this slide, this is actually the enablers of Industry 5.0. And of course, there are more than that, but this is just the top enablers. All right. So one of the key, very prominent item that pop up is actually the drones technology. So you can see all sort of drone technologies, and even it has been used in a Mars as a probe. The next one is actually in the exoskeleton, or something we call the biomechanics, that is integrating with the human body. And those actually also play a very important role in enabling Industry 5.0, that is human focusing on human integration. And of course, we have the additive technology, which is a material engineering that incorporating origami and also material science to achieve a higher level of flexibility. The whole words here is reconfigurable. So something, if you put it in a layman term, this is like a transformer, or what we call compliant material or compliant surfaces. Which means that you can do away all the joints, you can simplify the joints, you can do away all the bolts, all the nuts, you can simplify the actuating mechanism, therefore lowering the cost of manufacturing and also increasing the flexibility and the capability. All right. And the last element that is heavily utilizing technical origami is the mixed reality, not in a software aspect, but in a hardware aspect. So to that, let me just explain it very quickly with one slide. What is a mixed reality? Some of you might be quite familiar with this. It is actually a VR, AR, and MR. There are three types of virtual reality as a whole that we talk about, but technical origami is being utilized to realize a lot of technology and the deliverables in the mixed reality. So if you take a look at the mixed reality, is actually the interaction of the virtual element with that is providing the user some physical sensory. So we call this a multimodal sensory. So in order to do that, you need to have a lot of customization to individual user. So let me show you in a subsequent slide how technical origami is being utilized to integrate into realizing this element. One of the very fast-growing field in research and development is actually in the field of sensory, which is in this sense it's called haptics. Haptics is something that you want to induce sensory sensation to the user. For example, now in the VR, maybe you can see an apple or an object, but there is no way for you to feel the object. Is it a rough surface? Is it a hard? Maybe is it cold, hot? Or no? And also, if you press it harder, do you feel the hardness of the object? So in order to realize that, origami technology has been heavily investigated and also utilized in a lot of R&D projects. So if you take a look at the top left corner, there is just a summary of what the interfaces is functioning, the key function, and also how origami technology is actually helping it to be realized. I will show you more slides subsequently, but this is just a summary. So if you take a look at the center, which is the fold-away interfaces. So in order to transform or to transfer the information from the VR of the object to the user, you need to have touch or transformation of the information of the object to the sensory, to the touch. So in order to do that, you need to have a certain response. What we call this is kinesthetic. And a lot of time, it is something to do with whether or not you can integrate a lot of functions into physical devices. Not just one device, but multiple devices. If you take a look at B there are multiple degrees of freedom to give you a lot of knowledge feedback or the sensory feedback to the user. So let me elaborate slightly further. If you take a look at this fingertip haptics, haptics is something that is providing a sensory sensation to the user. So if you take a look at this fingertip device, it is actually using a lot of folding signs to realize the multiple force element that translated into sensory. In this sense, you have a shear sensation, you have a torsional sensation, and also you can feel pressure of the VR object. On the right-hand side, you can see that it's just a summary of to give you a rough idea of how that can be realized through folding. All right, of course, this is a very simplistic at the fundamental level. You can just see that this is just a flex circuit or it's a PCB. It's actually coated with a layer of membrane. It can be any other type of metal material. And you can see that as it folds, it will create torsional or even shear sensation. All right, and also by installing the spring, you can increase a lot of feel sensation. So let me just go through this to show you this short video so that you can have a better understanding. Take a look at the video that's playing on the right-hand side. So imagine that there is a device that you can wear at on the fingers, and you can see that it moves at a different direction using the origami haptics. It will induce different type of sensation onto the fingertip. All right, so imagine that if you enlarge this into a bodysuit, so you a different part of the body can experience a different force or the different sensation. You can code this and map this into the individual object in the VR environment, and therefore you are realizing what we call the mixed reality. All right, so you can see that you can go through a different type of frequency, torsional strength, and by having a multi-layer, well-folded, embedded origami structures, you can trigger them to produce a different type of sensation. All right, so there's a quick summary on this fingertip sensory device, what we call haptics. So another type of origami structured devices, this is under University of Hong Kong and University of Singapore, is that they are utilizing what we call the water bomb crease pattern in origami. So some of you that have done origami before, the origami balloon, or what we call origami water bomb, you can actually use that water bomb crease pattern. That is, you can see the water bomb crease pattern at the bottom left corner. That will give you a better understanding. Bottom left and bottom right is actually the multiple water bomb creases combined together to form a sheets of origami pattern. And you can activate the creases by either through actuators or even through a chemical process or a magnetic field. So for this device that you are seeing here is actually a device that you can wear on the wrist, and it can induce sensation onto the wrist. Of course, this It's only the illustration done on the wrist. Of course, you can just enlarge this to the whole bodysuit or even the whole chamber, what we call the mixed reality chamber. And if you take a look at the top right corner, you can see that by carefully folding the water bomb into different shapes and different formation, it can actually stimulate different type of sensation, right? Sensory sensation, linear pitch, roll, diagonal array. So you can see the graph there. That is how it can be induced. So this is the benefit of the origami and flexibility of technical origami. And if you replace the material from paper to any other type, then it can actually fulfill the usability of the end environment. All right. Okay, just let me check. If you have any questions, do type it in the chat so that I can maybe if you have question on this particular slide that I'm talking, so you can just put it into a chat so that I can immediately address the question. All right. So I think it's easier to relate to this rather than after finish, you might have forgotten about some of the slides that I talked about in a earlier time. All right. So if you take a look at the fabrication process for the haptics that is wearing on the wrist, it's actually quite simple, and you can see that it's readily been mass produced at a reasonable cost. Of course, the only challenge here is the reliability of the device, because this is actually a device that is changing shape and reconfiguring and redeploying from time to time. So the wear and tear of it will be a key challenge through the material selection. But these two slides is just to illustrate to you so that you have an idea how the folding science can be utilized to realize the technology in haptics. Next slide is actually our very own, or Utah very own student. She's one of the active member of the Malaysia Origami Association and also the Malaysian Origami Artists. She has just recently been awarded the Best Engineering Student Award from the IEEE. So if you take a look at the origami technology that she has used to integrate into her final year thesis, you can see how the so-called simplistic origami crease pattern, what we call Miura fold here. If you take a look at the bottom right-hand corner here, Miura fold has been around for at least 35 years now, and it has found its way into many applications, from a solar panel of a satellite to the subway map, to surgical stents for the heart surgery, to molecular level to create a scaffolded DNA. And now it's actually finding its usage into a biomedical science and also biomedical instrument. So this is a very simple and very good illustration of how origami can be used to realize a biomedical instrument. So this is actually a hand or finger rehab unit. So I will show you this quick video so that you have a good understanding of how it's been utilized.
From the best of our knowledge, this design is novel and has not been attempted before. Miura vertex is a type of vertex that contains 4 intersecting creases, while origami string is a template that contains multiple Miura vertices. The origami string template that was specifically designed for this project contains 3 Miura vertices, V1, V2, and V3. As you can see here, they have 55, 45, and 30-degree angles respectively.
So the idea is that you are utilizing the folding signs at 3 locations here. Miura is named after the creator of, or the discoverer of this crease pattern. It has to be formed in a certain formation. The blue line and the red line respectively, they are representing the valley fold and mountain fold. Valley fold being the lines being sinking into the surface of the material, and the red line representing the popping up or the convection of the material from the surface. So convection and also concavement of the surface. So by using this combination, you can actually control the direction of that piece of homogeneous material. Of course, in this sense, in order to increase the flexibility, the homogeneous material is replaced by a 3D printed PCB and also actuator. So let me continue. I will skip a little bit because of time. I will skip a little bit of this slide or the video so that you can go to the point of interest. So if you take a look at this concept, it will give you a very good understanding of how one piece of so just one piece of material, by introducing 3 folding points, you can actually change the direction. All right, and if you translate this into a PCB, a 3D printed PCB and actuator, then you can realize the movement that is required. So let me just skip a bit to the front.
Currently, the transmission mechanism lies flat. As you can see here, the servo motors will be attached to the side panels in this segment of the transmission mechanism. When the arms of the servo motor rotates upwards, the side panels would also move up. Force will be transferred to the subsequent segments of the transmission mechanism, and it will fall like this. This will generate extension at the radiocouple joint and flexion at the PIP and MCP joints. When the servo motor rotates downwards, the transmission mechanism will move back to its original position, causing the radiocouple joint to rotate back to its original position and the PIP and MCP joints to undergo extension.
So now let's take a look at how it looks like in the actual fabricated prototype. So let me just go back a little bit. All right. So the beauty of this is using origami technology is you are able to significantly simplifying the mechanism and therefore reducing the cost to make it able to be commercialized. So a lot of challenges at the earlier stage of the technical origami renaissance period after World War II is that it's very expensive and it's very difficult to be implemented. So over the last 30, 40 years, the advancement in the origami technology intellectual field has actually, they have discovered a lot of theorems, a lot of axioms, a lot of rules that you can use to construct a more efficient model. So by using that Miura flow is actually one of the more efficient one that you can use to reduce all those costs. Next, maybe some of you having a question is that what is deployable or what is a reconfigurable origami? So if you take a look at the screen, I think it's very self-explanatory. Something that is folded from a piece of paper, but you can reconfigure the shape or you can redeploy the shape. So that is what is deployable origami. And if you take a look at more examples, some of you might be able to associate this with some of the high-tech instrument that you are seeing. For example, the solar sail, solar panel. You have pneumatics for automotive, mechanical engineering, and even architectural cladding. So those are deployable origami. And of course, there are a lot of ways to test out your idea before you having to spend hours and hours of time to fold using a paper, then to find out that, whoops, this doesn't work. So there are a lot of free software out there, at least 8 to 7 types of freeware that you can easily use to plot out your idea and to check whether someone has already patented it. Or you can also test out your idea whether it can be reconfigured, that it meets all the rules in origami. So for those of you who like to dwell deeper, maybe in the future, if we have an opportunity, I can conduct a quick intensive class to keep you up to date. What are those key content? What are Maekawa theorems? What are Kawasaki theorems? What are the flat foldability? What are the interchangeability of one or more, or two or three or more degree of freedom? How do you use one piece of media? It can be paper, metal sheets, and you can superimpose different types of crisp pattern onto one piece of paper. So meaning that that piece of material, it can be reconfigured into 1, 2, 3, or even more shapes without having to use a different piece of paper. So essentially, you are integrating multiple functions onto a piece of homogeneous media, all right? So that is to give you an idea. And if you take a look at the screen now, of course, it's just one type, one paper type only. So one paper is for crane, and the other one, the rectangular one, is for the train. Of course, it's without cutting and without gluing. Of course, you can actually superimpose two of them into one piece of material, and they can walk into a crane and also a train without having to use two separate pieces. So this is actually what we call the reconfigurable. So essentially, to make it easier for people to understand, you just imagine the transformer from a car to robot, something like that. All right. And if we go deeper and to find out from the industry, you can see that this is from NASA Jet Propulsion System. As we speak, this is actually in progress right now. They are trying to send a solar sail to the outer space to block out the brightest spot from the given galaxy, so that the space telescope can capture the images of those planets behind the sun of that galaxy. All right. And also it has been used in engineering. This is actually used to realize the function of a bellows in order to cushion the impacts. So let me just play this short video so that you have an idea how technical origami is playing a role in the engineering.
We work on designing and fabricating novel materials and structures. Large number of mathematicians and computer scientists, engineers are working on origami nowadays. So imagine that you're going to use this origami structure as impact protection layer, and you are applying, let's say, impact on one side. The compression wave will eventually change into a decompression wave while it's moving through this chain. So this video clip shows at the beginning of impact, we have this red color formed due to the compression, but immediately after that, we have blue color due to the bouncing back motion of origami itself. But what is interesting is, at a certain point, we see blue color ahead of red color. What you are going to feel on the other side of the structure is that the bouncing motion first, instead of the compressive force. So what you're going to feel on the other side is more like pulling motion instead of compressive motion. The application can be abundant. For example, delivering a package using a drone. You want to protect your medium from the impact from the ground. And another example can be landing structure and touchdown. We can convert compression to tension, so your whole structure can be well protected against the impact. When I have visitors from outside and they look at these variety of origami, they're just amazed to see how this interesting origami can be integrated into state-of-the-art research. When we were starting this project, the mechanism seems so counterintuitive. So we were so excited, so thrilled, because we were not even sure this can really happen.
Right, for this bellow crease pattern, if you take a look at this crease pattern on your left, you can actually just print this out, and maybe like less than 20 minutes, you can fold it. And the top left corner is showing you how it changes from a compression to a pulling force. So it's quite amazing. It's actually from just one piece of paper. By twisting it, it will follow the Kressling pattern. This is called actually the Kressling collapse pattern. If you search the internet along this keyword, you can easily find the crease pattern. And for those of you who are interested, you can just print it out. 20 minutes, you can do this. You can take a look at how it actually changes. Right. So next is also similarly, is also this particular structure, but how it's been utilized in constructing medical devices. So this is where the monies are all in. So let me show you this. This actually been adopted by Da Vinci and so on, those microsurgical medical instrument manufacturer. So take a look at how it can be used as a chef buckling. All right. So let me just play this.
Guide that supports flexible endoscopes and catheters during robotic surgery. An array of triangulated cylinders, each designed to either provide motion or dictate the buckling mode of the supported instrument. By customizing the parameters of each layer, the OriGuide exploits unique energy properties of the pattern to create a collapsible mechanism with a constant inner diameter for support and a constant outer diameter during motion. This integration of monostable and bistable layers also enables the OriGuide to be fabricated from a single sheet of disposable material.
All right, so by changing the material to a more durable one, it can actually increase the product life, and therefore it can be easily manufacturable and incorporated into our current medical instrument technology. Let me show you again another type of origami, which is called rigid foldable origami. So the word rigid is when you increase the thickness of the media. In this case, it's paper, and also the hardness. So when you replace it with, let's say, PCB material, a thicker structure like a metal piece, plastic sheets, you need to change the design a little bit. You can no longer use the crease pattern that you used to fold on a paper. So all this technical content is called rigid foldable origami, and there are a lot of research theses being written on all the factors and the rules and the axioms and the theory on how you should go ahead to implement the crease pattern when you move from paper to a thicker material. So let me just show you very quickly this short video.
Foldability of origami twists. This work is laying a foundation for being able to do rigidly foldable tessellations that could be used in deployable structures made out of materials other than paper. This is a degree 4 vertex that has 4 creases that meet at a single point called a vertex. A flat foldable vertex is one that can be folded into a second flat position. A rigidly foldable vertex or origami pattern is one that the pattern can be folded without any deflection of the panels, with all of the deflection only occurring at the creases. An origami twist has a central polygon that then has creases extending from each vertex of the polygon, and those creases extend from the central polygon at the twist angle, which is the same at each vertex. A rigidly foldable origami twist would be an origami twist where all of the creases can occur without any deflection of the panels.
This paper presents a straightforward mathematical approach to determining if a twist is rigidly foldable. This can also be used to design new origami twists that are rigidly foldable. We present and prove a number of theorems, such as that there is no origami triangle twist that is rigidly foldable. We also have proved a number of theorems regarding rectangular and square twists. Isosceles trapezoid twists. The twist angle would be to create a rigidly foldable regular polygon. We have organized a table. Twist angle can be used in a number of possible future deployable structures where the panels are made from structural rigid materials.
So this is a square twist. It's just one type of twist pattern that can realize the rigid deployable structure. So there are tons of twist patterns out there, and as we speak, there are origami scientists that are discovering new formation and new twist pattern that can also fit into realizing the rigid origami. So in the IP field, if you go to Google IP and you type in origami, and if you take a look at the timeline, you will see that for the last 5 years, origami intellectual property growth in the IP landscape is actually doubling, tripling, and I think just for the last 6 months, you can see that it's already doubling in 6 months' time. So I think a lot of corporation, a lot of learning, higher level learning institute, they are betting on their grant money into this field. Also, this is still on a rigid foldable structures. This is another type of mechanism that is quite popular right now in a lot of universities. So I think that it will be knowledgeable for you to know this. So let me share this short video.
This paper discusses capabilities of the offset panel technique and verifies the method and capabilities in hardware. The offset panel tells the kinematic behavior and the range of motion of an origami pattern. Fifth configuration shows that the panels in a single model can each be assigned different thickness. Capabilities such as these make the offset panel technique a strong candidate for origami-based applications.
So the meaning for offset is that when you are transferring the crease pattern from a thin paper to a thicker, rigid material, you need to know how to offset the crease pattern to create clearance, so that when you fold, the thick material has the clearance to fit into a different folding formation. So there are a lot of rules into how to design this. And if those of you who are interested can take a look at some of the courses that we are offering in Origami Academy, all right? Next, we talk about deployable structure, the mechanism. So those crease pattern, again, you can activate the crease pattern in using all types of mechanism, right? You can use actuators, you can use coated chemical that can respond to magnetic field. You can use enzyme to trigger some of the atoms if you are building the crease pattern with a certain type of protein cluster at the microscopic level. So this is just a summary for you to look at how to transform the crease pattern into a movement structure. All right, you have a straight scissor structure, you have a curved scissor structure, you have a radial scissor structure that you can easily utilize the origami crease pattern technique into realizing the mechanical movement mechanism. And again, if you take a look at this summary slide, it will give you a better understanding. All those red lines are, of course, just one type of color, but of course you can map it into convection and also concave lines. Convex is actually to popping up from the surface. Concave is popping in from the surface of the metal or the media. So if you are able to map that into or design it into any piece of media, you are able to make it move. All right. So in a nutshell, this is reconfigure. You can make it reconfigure. You can make it you can make it deployable or redeployable, because before you deploy, usually you want to fold it first. So usually you see the word redeployable rather than just deployable. All right, so let me show you a little bit of a live example in the industry, how this has been integrated into the high-tech industry. So one of the, probably this is a already overused slide that a lot of you might have seen this, the solar panel deployment mechanism that helps it to open up, and this is utilizing the Miura fold. The other one that is less known of is actually the deployable giant structure, the umbrella that can be found in Medina in Saudi Arabia. And you can see that it's actually hydraulically controlled, and underneath the umbrella you have all these rooms to run the engine. All right, so you can quickly deploy the foldable umbrella, and you can cover the area more than 1 million square foot area in just less than 10 minutes time, and you can reduce the temperature up to 10 degrees C. So this is proving to be very useful. And when it rains or when you want to shield from the heat of the sun, you can also use that. Okay, so this is the one example. The next one is the world's largest sun responsive adaptive facade. This can be found in Abu Dhabi, and it has more than 2,000 origami kinetic solar panels, and individual panels will respond to a certain condition that you can program in, temperature, light intensity, and also it can help to feedback to the environment inside the building. So by having an AI system to communicate the internal control parameters with the facade, the origami facade, you can control the amount of light and therefore heat going into the building. And at night, it can show as a LED display panel. All right, so this is one of the most famous, perhaps one of the most expensive solar origami responsive adaptive facade. Next is actually drones. Just now you saw the enabler. One of the enabler for Industry 5.0 is actually the drone technology. Actually, there are a lot of requirements on drone technology nowadays that it needs to be very agile and be able to morph in a shape so that it can fit into a different type of environment. So let me show you this very quick short video so that you have an idea how origami has been used to realize the agility in drone technology.
The novelty of this robot is that it can fold and unfold the arms very quickly in about half a second and fly off. And this is very important because flying robots need to have a certain size for the propellers in order to carry some payload. Now, if you have an unfoldable robot, you can simply fold it, put it in your pocket, or carry many of these small robots in your backpack, and then go and use them wherever you need very easily.
This quadrotor is equipped with 4 foldable arms manufactured according to an origami technique. Deployment is driven by the force which are generated by the propellers. So when the propellers start to turn, the arm unfolds, and then magnets enable the engage of the horizontal fold, and the arms are now fully deployed and the quadrotor is ready for flight.
Foldability is a very important question in my lab, a research question, because it applies to all drones. The principles that we have seen in this small robot need to be generalized to any type of drone with wings or with protective cages.
So the flat foldability and redeployability, if you know it enough, you can easily implement this in drone technologies. As we speak, I've been engaged by one European design company to actually collaborate with them to design a deployable receivable net for the automated drone delivery of the Amazon Europe. So as you know that right now the delivery they want to do a drone delivery. So if you order something, a drone will come and then there is a receptacle at your apartment or your house or your balcony there that you can receive the product. So the problem that they have is that when the drone drop the product due to the wind factor or the accuracy, the stability, or even the shape of the package, sometimes it cannot be dropped into the receptacle accurately. So they want to have some form of a deployable type of receiving nets that can increase the surface a little bit, so that even though the package that they drop is actually skewed to one side, it still have some tolerance to be able to capture it and then slide down into the receptacles. So yeah, they are actually collaborating with me to find out whether or not there are any novel script pattern out there that people have not been patented that they can do. So knowing what has been patented and what has not is actually a very powerful knowledge and also important knowledge, because you don't want to do something and then to find out that, oh, that has been already patented, all right? So to share with you that this can be done and it has a lot of application and a lot of opportunity. The other one is called haptics that you have seen, but this time is you can see the live example rather than just a diagram. So let me just play this short video so that you can see.
Our device is a foldable haptic interface. Its pocket size stays in your palm, and it gives to the user the sense of touch when exploring a virtual environment. Most of the interfaces in the market provide only a vibrational feedback to the user. There are some devices that can provide forces and stiffness perception, but they are very costly or they are quite bulky. Our system can provide the same kind of stiffness perception, texture perception, but in a very small scale and for a very affordable cost.
This is adjusted for virtual reality. It allows to perceive the virtual objects. You can touch them, you can feel their stiffness, you can perceive the contour and the texture. And this is thanks to this device that you see on top that can apply accurate force feedback under your finger.
The biggest advantage of using Origami Robot platform to recreate any type of robotic system is due to its nominally flat layering process. Nominally flat layering process allows us to have multiple layers, different layers, either let it be a circuitry, sensors, actuators, or kinematic linkages into a single platform, allows us to,
for example, and in general.
All right, so due to time, let me just browse through this so that we can have enough time for the wrap up and questioning. So I just want to, there are more slides that will easily run for another hour, but I will just skim through the important one that I would like to share with you. So this is another technology that is being pioneered in Korea. This is the shapeable and reconfigurable wheel. Some of you might have seen this before. So we can see that by using the crease pattern, you can fold and unfold and change the topology and the structure of the wheel surface to fit to any terrain or surface condition. All right, so it's actually use a multi-layered structure or material, but basically it's you utilizing the same crease pattern. And the crease pattern you can see on the right-hand side that you can easily print out using a printer and take a piece of paper to fold just to see how it actually change shape. So that is actually quite interesting. And the other one is actually the James Webb Telescope. Not sure whether how many of you know, there are about 60 patented origami patterns being used on board of James Webb Space Telescope. And you can go to NASA James Webb Telescope site. You can actually print out this origami crease pattern from the mirror array, and you can just fold it in less than half an hour. Again, this is another usage of origami to construct the bulletproof shield, and it has already been implemented in some states in US back in 2020 April. So it's actually using a Yoshimura crease pattern that you can see on the top right corner there. Again, you can easily print this out. One of the Utah senior, right now he's in a postdoctorate. He has done a actual mock-up, a large one, and before the MCO lockdown. I think the last one is 2019. We have an origami workshop and also exhibition that he actually brought it there to show how you open up. So you can easily print this out, the crease pattern. The second one right here, using a printer paper, and you can play around with it. The solid line is the mountain line. They are popping up from the surface of the paper, and the dotted line is sinking in. All right. And again, the other hot topic in technical origami is what we call developable surface or compliance mechanism. And you can see that this is you can imprint the structure onto a piece of metal and you can flat fold it. All right. So I think we are running out of time, and I will pass the floor back to Kingsley. Kingsley, you want to go for the Q&A session, right? Kingsley, are you there?
Yes, Mr. Kenneth, yeah, I'm here.
All right. So is the last of my slide. So now is opening to a Q&A session. Any question from the floor? Anyone? Any particular slide that you like me to re-show again so that you can refresh your Okay, there are a lot of information to squeeze in just 1 hour. So usually for Sunway University and the One Academy, usually I will take up about 4 hours, including a hands-on session. Today we are just trying to squeeze in more information. There are a lot more information that I couldn't share in just 1 hour. But I think hopefully you can get the idea of how the deployable reconfigurable origami is being utilized in the industries. All right, and already in Utah specifically, we have 2 students already that already have their senior year thesis being peer reviewed by the engineering community and been accepted already. So congratulations to Utah. And of course, Utah is not the only one. Perdana University on UITM, they already have a couple of very simplistic type of origami patent 3 or 5 years ago. But those are not in a high-tech industry. Those are more on a very simplistic structure for the handphone casing, also for the safety device to cushion the weight during the fire when the house collapsed. So for the really high-tech application, I think the 2 papers from Utah students, yeah, they are actually right in the core there. So congratulations to Utah. All right. Any question from the floor, anyone? If not, I'll pass back to Kingsley.
All right.
Thanks for your time. All right.
Okay. Thank you, Mr. Kenneth. Okay. For students and Utah staff, kindly fill up the sign-up form and feedback form after the webinar. Yeah? We would like to take a group photo with everyone in this webinar. Please turn on your camera and stand by. Participants, please turn on your camera so we can take a group photo. In the count of 3, 2, 1. Okay, we take another one with the freestyle. Wait a moment. Okay. Can we take another one?
Kingsley,
Yeah, I think, yeah.
Louis mentioned the camera function is disabled for participant. I think they couldn't turn on.
I see. So we try another one. Take another one.
Sockbill can turn on already. I think the rest might not be able to turn on.
Everyone try again.
I think Miss Lee already enabled the function, right?
Yeah,
if you can, yeah,
we enable that.
you can turn on your camera and give it a try. Still can't.
I think can already.
Okay, some of them can already.
Everyone ready already? Still can't? No, we just enable that. Maybe try again. Maybe Mr. John Lee can try again. Okay, in the count of 3, 2, 1, we take one. Okay, this will be the last photo session we are taking. Freestyle this around. 1, 2, 3, 2, 1. Okay, thank you everyone. Thanks, Mr. Kenneth. Anything
Thank you.
Is there anything you want to cover before we wrap up?
That will be all. I mean, for those students in Utah or any university or even school that if you're interested, you can contact me directly. And I'm actually doing lecturing services to a lot of university and schools. All right. Yeah, that's all. Thank you for your time. Happy folding.
Dear
Thank you.
participants, we will have the upcoming webinar, which will be Human Brain versus Computer Brain by TS Tai Si Chiu, right after this webinar, yeah? So stay tuned. Thank you everyone and stay safe.